This video is about fundamental theorem for the line integrals. Okay, you have to read the book first. Okay, this is just a supplement to help you understand the book. Okay, fundamental theorem of the calculus is something like this. FB minus FA. Small f and capital F, they have a relationship like this. Capital F, you take derivative, give you small f. In the other words, capital F is antiderivative. Okay, this is called fundamental theorem of the calculus. Today we're going to learn fundamental theorem for line integrals. Okay, there's two kinds of line integral. We said one is like the work has been done. Okay. For example, the work has been done can be defined by second type of line integral. F here is a force, is a vector. dr there is a displacement. Here is a c. Okay, this is a curve C. And any curve can be described by a parametric equation R. This point is R A. T equal to A give you this point. This point is R B. In other words, T equal to B give you this point. Okay, force times displacement give you, what we do is like, small one, right? For each one, you just add them together, take a limit. That's what it is. Okay, my force here is a vector field with two components. Three components, same thing. Okay. Or you can write Pi plus Qj. And this integral f dot dr really is, f here is a p q dot product. Okay, dr is this displacement, really can be written as dx and a dy here. So dr is a dx and a dy. So you perform the dot product, what give you scalar is a p dx plus q dy. Okay, we say a vector field F is conservative if F can be written as a gradient of small f. Small f is a scalar function. Let me give you an example. What do we mean by that? For example, my f is a vector field. It's like y here, x here. Now the question, can you find small f such that gradient small f give you y of x? So for this one, it's not hard to see if my small fxy is equal to x times y. What is gradient f? Gradient f is a partial f respect to x. Gradient f is a vector. Okay. How many components depend on your f depend on how many variables. If my small f depends on two variables, then gradient f is a vector with two components. Second one is a partial f respect to y. Okay. Now let's take a partial derivative with respect that. Okay, take a partial derivative with respect to x. You treat y as a constant. Okay. So give you y. Then partial f respect to y give you x. So for this capital F, we obviously can find small f such that my capital F is equal to gradient of small f. If this is the case, we say capital F is a conservative vector field. Obviously, not all the vector fields are conservative. However, if your vector field is conservative, then this line integral can be defined differently. If this is conservative, that means you can write gradient f times dr. Then this can be defined. This line integral can be defined by f r b minus f r a. In the other words, this point is R A. This point is R B. Okay, this curve is R of t. Okay, so this is C. Okay, if your line integral along this curve, what really matters is endpoint and starting point. Which curve you go, which path you go does not matter as long as they have the same starting point and end point. Say this is C1, C2. This line integral, you can go with any curve. You will get the same answer. Okay. So if this is true, we say this integral is independent of the path. Okay. Obviously, okay, under certain condition. On a certain condition, you have to read the book to find out what are those conditions. On a certain condition, the following things are equivalent. The first, f is conservative. What do we mean by that? It means f can be capital F, it can be written as a gradient of small f. As you can see, if f is conservative, then this line integral will be independent of a path C, right? You can tell that only endpoint and starting point matters. The rest of things does not matter. And the line integral independent of path is equivalent to, say, this line integral equal to 0 for any closed path C. Okay, what do we mean closed path? It means like that. For the closed path, your starting point and end point will be the same. So the difference will be the same. That's why you got 0, which is it's not hard to understand. Okay, so we call this sense is a fundamental theorem for the line integrals. Okay. Now, this tells you if your vector field capital F is conservative, then you can find a small f, then you can find this line integral just by evaluate at 2 points, just like fundamental theorem of the calculus. Okay, so how do you know for given vector field capital F is conservative? Now we have a very simple way to check that. Also under certain condition, okay? Then this is also equivalent to my f there is a p and a q, okay? Now, if partial p respect to y equal to partial q respect to x, then if this is true, then your capital F is conservative. Okay. So let me say that again. The following things are equivalent under certain conditions. Okay, first, if f is conservative, means capital F can be right gradient of small f. You are able to find a small f such that it's true. Okay, if this is true based on the fundamental theorem for the line integral, then to find this line integral, what you need to do is find small f and evaluate a starting point and end point. Then you are done. So this means this line integral, you go which curve does not matter. As long as they have the same starting and ending points, then this line integral will be the same. Okay, which is equivalent to say if your curve is closed. That means your starting point and end points are the same points. Therefore, this line integral would give you 0. Okay. The last condition tells you how do you tell for the given vector field capital F is conservative. It's very easy to, as long as you know how to take a partial derivative. You just check partial p respect to y and partial q respect to x. See they're equal or not. If they're equal, then it's conservative. Okay, now let's look at some examples. Example, I give you capital F, I give you vector field xy equal to y e to the x plus sine y I, that's first component, plus ex plus x cosine y j. Okay. Now the question is f conservative? Okay. In the other words, can you find small f? Okay. Now we have two questions. First of all, check this one is conservative or not. Then, if it's conservative, then let's find such a small f, such that capital F equal to gradient of small f. Okay. Now, this is true only for conservative vector field. So you better check your f is conservative or not. You are not trying to look for something which does not exist. Okay. So how can we tell f is conservative? So what do you need to do? Just check that equation. For this specific problem, my p here is the first component is y ex plus sine y. My q here is e to the x plus x cosine y. Okay. So find the partial p respect to y. Whenever you see x, you treat it as a constant. So take the root of first one, give you e to the x. Second one give you cosine y. Partial q respect to x, give you e to the x. Then this time you treat y as a constant, give you cosine y. Okay. Now, obviously they're equal. That means f is conservative. Now, when you do your homework, you better take your partial derivative correctly. Otherwise, f is conservative, then if you did something wrong, then your conclusion could be totally different. Okay, f is conservative. That means we can find small f such that this is true. Okay. Such that this is true. Okay. What is the gradient f? Say that again. Partial f respect to x, partial f respect to y. What is the capital F? P and Q, right? I give you P there, Q there. Okay. So this means you have two vectors are equal. That means the first component is equal to P. The first one equal to the first one. What is my P? P there is y e to the x plus sine y. Then the second component equal e to the x plus x cosine y. Okay, now we're looking for the f. We're looking for small f. Make both equations satisfied. Okay. Now let's look at the first one. Okay. Let's look at the first equation. We're looking for f. Make this equation satisfied. Okay. So the first thing we do is integrate on both sides of the equation respect to x. Now this is the x, this is the x, give you f. Okay. Now this is what we call antiderivative. Okay. So if I don't plus anything, this is just a antiderivative. For given function, how many antiderivative we have? Recall that it's infinite many. It's infinite many, so we want to find all of them. Okay. Why we want to find all of them? Okay, if I just stop here, we find a function such that the first equation satisfied. Now we're not sure this is a function that will satisfy second equation, so we need to find all the functions, make first equation satisfied. Then among those, try to find something the second equation satisfied. That's why we need to find all. So should we plus c there? C is not enough. Plus cy. That means this thing can be any function of y. Okay. Why we can do that? Because take a partial derivative. Okay. Take a partial derivative respect to x on this equation. You are going to see c's of y will be gone. Okay. All right. Now let's find this. So now let's integrate it respect to x, which means you treat y as a constant. Okay. So it means first one you can pull the y out. Just integrate ex, give you e to the x. And the second one, treat y as a constant. Just like you integrate 1, which give you x, right? So x times sine y, then plus c's of y. Okay. Okay, you are going to see. Doesn't matter what is the c's of y. C's of y could be y squared sine y. Doesn't matter what it is. If you take a partial derivative of this equation, that will make your first equation satisfied. Okay. Now we want to choose c's of y such that partial f respect to y give you satisfy second equation. Okay, let's do that. So what I'm doing now is to take a partial derivative of that equation respect to x on both sides. So when you take a partial derivative respect to x, you treat y as a constant. So you got e to the x, you take a derivative, give yourself. No, we're talking about respect to y, sorry. Okay, take a partial derivative. We want to check the second equation. Okay, we take a partial f respect to y. Okay, you treat x as a constant, so this is gone. Okay, then plus second term, you take a derivative respect to y. You treat x as a constant, so give you x cosine y. Then plus c prime of y. Okay. We want this one make second equation satisfied. What is the second equation? Partial f partial y equal to e to the x plus x cosine y. So this implies c prime y equal to 0. Okay. Therefore, it's not hard to see if I chose my fxy equal to y e to the x plus x sine y. Then this will be right function because check that. Okay, I want you to check that gradient f would give you capital F. Then we're done. Okay, now let's look at another example. This example, we give you a function, vector field, x squared I plus y squared j. And we give you C here. C here is part of a parabola 2x squared from point -1 to 2 and 8. Okay. What does my curve looks like? X and Y is a parabola. Say here is this point, -1 and 2, and this one point here is a 2 and 8. Okay, this is our C. Also, any curve can be described by R, right? RT. So what's our RT here? Okay, if they give you a curve like that, you always can write x equal to t, y equal to 2x squared. Since x equal to t, so this gives you 2t squared. That's your R, okay? My R's of t here equal to t and 2t squared. Okay. And my R's starting point is R. This is x equal to -1, right? -1. What is my starting points? Replace t by -1. T squared give you 2. My end point, R's of end point is 2. Give you plug in x by 2, you got 2 and 8. Okay. Now, we got two questions. First, we want to find, is f conservative? Yes. If it's yes, find f, small f. Then B, we want to integrate this line integral, f dot dr. Okay. I'm going to integrate this line integral using two ways. Okay, first let's see f is conservative. Okay. What is my f? My f here is x squared, y squared, right? So p here is x squared, q here is y squared. F is conservative or not? Check this. Partial p respect to y give you 0. And partial q respect to y give you respect to x also give you 0. So they're equal. That means f is conservative. Okay, now if we want to use fundamental theorem of the line integral to find this line integral, we need to find the small f. Okay, now let's find small f. We know such small f exists. Okay, what do we mean small f? That means this is true. Partial f respect to x, partial f respect to y. My f, capital F is x squared, y squared. Okay, so first two vectors equal. First component equal. Second component equal. Give you two equations. Now let's start with the first one, okay? So we integrate first equation on both sides respect to x. They give you f. Remember, you have to plus c sub y. Okay, so this gives you 1/3 x to the third plus c sub y. For any c sub y, this f will satisfy first equation. You can check that. Checking that by taking partial derivative on that equation, you are going to see first equation satisfied. Okay, now we want to choose c sub y to make second equation satisfied. So what I'm doing now is to take a partial derivative on this equation respect to y. Okay. Now I have two terms. Take a derivative of first one with respect to y. Treat x as a constant, give you 0. Then plus. Take a derivative of the second one, give you c prime of y. Okay, we want to make the second equation satisfied. That means it would give you y squared. So that means c is a function such that you take a derivative, give you y squared. Therefore, my c of y, you integrate on both sides, give you 1/3 y to the third. Okay, so we find out fxy, which give you 1/3 x to the third plus c of y, which is 1/3 y to the third. So by using fundamental, now let's do part B. Okay. Part B, we want to find this line integral. By using fundamental theorem for line integral, this gives you f r's of b minus f r's of a. So I showed you before. R's of b there is f 2 and 8 minus f minus 1 and 2. That's starting point. So you just plug in here xy by 2 and 8 or 1, 2 would give you calculate that to give you 171. Okay. So we use fundamental theorem for the line integral to find this. Now let's do that again. Okay, we know how to do this, right? By learning something in the 17.2. This is c p dx plus q dy. Okay, for this case, my p here is x squared dx. My q here is y squared dy. Remember, my curve here, you always need to find this parametric equation. Okay, it's a t and 2t squared, right? Okay, so x equal to t, y equal to 2t squared, so your dx equal to t, your dy equal to 4t dt. So we can integrate this one. Now, t equal to minus 1. T equal to minus 1 give you the starting point, right? And t equal to 2 give you end point. Replace x by t, so you got a t squared. Replace dx by, dt. Dx equal to, okay, x equal to t, dx equal to dt, I'm sorry, dt, okay. And plus, minus 1 to 2. Y equal to 2t squared, square that to give you 4t to the fourth. Then dy equal to another 4t dt. Okay. So this one, you integrate this to give you 1/3 t to the third. You evaluate minus 1 to 2. Then plus. This is 16. Then integrate of t to the fifth, give you 1/6, 2 to the 6, evaluate the minus 1 to 2. If you calculate that, give you 171/2. Okay. So this just tells you, I give you this example just to verify the fundamental theorem of the calculus of the line integral is right.